involved in climate for over a decade. And I started as a bit of a skeptic, but I'm going to share a little animated video. There's a static slide that I'll get to momentarily, but this rotating globe shows essentially the 30 years of history that we look back at, the 60s, 70s, and 80s, and we've been comparing them to the 90s, the 2000s, and the 2010s. And that's what the Actuaries Climate Index that I've been a part of does. That was just too cool of a presentation done by some people I've come across not to share. It looks a little better animated than it does in my presentation. I'm trying to pull that up here. Da-da-da. Here we go. This is a shortened version of a presentation on the Actuaries Climate Index I gave a few months back to the Caribbean Actuarial Association. They are one of a number of organizations around the world that have taken the Actuaries Climate Index, which you'll learn more about. It started in North America. I was a part of the launch team. Here's an outline of the presentation that I'm going to walk through quickly here. You saw one snapshot of climate history, the nice animated globes. I'll show you a couple more key snapshots that have helped me understand how climate has really warmed the globe. And then I'll give you a look at the past and present of the Actuaries Climate Index. It's focused on North America, as you'll see. I'll tell you why, who did it, how, when it happened, what's happening. And then I'll give you a peek at what I'm hearing from contacts I have around the world, how the Actuaries Climate Index is expanding. And I'll give you some sneak peeks at how we are going to be improving the Actuaries Climate Index. It's 6 parts. And I'll conclude with a look at an unexpected finding about sea level rise that we saw in North America that is really affecting the globe. So with that introduction, let's take a look. This is almost a $1 million, a 1 million year history graph. Right about 1950, you'll see Charles Keeling started taking a look at CO2 and he saw it warming. He measured CO2 as its rare amount in our climate. As you can see, it just averaged about 300 parts per million. The gradual increase got people to look back, and you can see back for 800,000 years, it has stayed under 300,000 parts per million. And it's gone up and down with some cycles I could explain, but I'm going to avoid all that nuanced history. And this is Charles Keeling himself. In the 50s, he worked for the Scripps Institute out of the University of Stanford in California. And he got some fancy scientific instruments that measured precisely the parts per million of CO2. And it started going up and then it dropped, and he thought his instruments were broken. But lo and behold, what he found is the Earth actually breathes. The plants, many of them in the northern part of South Africa, in the Amazon there, especially, breathe in the carbon dioxide every year that we've exhaled a lot. You can see how industry has greatly increased and accelerated the rise of CO2. And this is a snapshot of that graph I let you see on an animated basis. You could follow the link in this presentation. I've given a copy of this to Thomas and Anna, and I welcome them sharing that. Here's a preview of the Actuaries Climate Index that I've been a part of since, oh, it's over a decade now. It really got launched about 5 years ago in 2016. You can see it has two halves that really parallel the base year period, the 60s, 70s, and 80s. That's the left half of this graph of the ACI, and then the warming years. You can see the 90s, the 2000s, and the 2010s. The measurement we've been doing, you can see it has just increased. Why have we been doing it? Here's why insurers have cared or learned to care. In the 80s, this is from Munich Re, one of a couple reinsurers and a big broker house, Aon, and the Insurance Institute of America have tracked how many worldwide extreme weather catastrophes. Were I giving this in the US, I would have similar graph for North America, but given I was invited by Thomas and the University of Guyana, I pulled out these worldwide stats. The simple message of this graph is since the 80s, catastrophic events have tripled. You can see there were about 200 in the 80s, climbing to almost 300 in the 90s, 400 in the late 90s, and early 2000s. There was a bit of a cooling period, and then in something happened that we're still trying to explain long about 2005, 6, and 7, that there was a really noticeable increase in catastrophic events. You can see the blue bars are floods and mudslides. The storms are in the tan bar segments. And extreme temperatures, droughts, and fires haven't been so obviously increasing. Pardon me, I need to take a little drink here. So that first graph was how many. Here is how much these catastrophe events have cost, and where the number of events have tripled, the cost has really quadrupled from $500 billion in the 80s to literally $2 trillion during the last decade. The latest I have from Munich Re, they stopped sharing their information as widely, ended at 2018. So I've really got a year of overlap if you're precise. But I know from personal dialogue that from 2010 to 2019, there literally were 2 trillion of catastrophe events around the world, which you can see in red were geophysical. There are some increasing number of earthquakes, meteorologic events. These are thunderstorms in the US and the like elsewhere. And then there are hydrological, which includes floods and so on. And then climate events, which are droughts and wildfires. So you can see they've tripled. Pardon my dry throat. I'm fighting a bit of a cold, which I'm glad I can't share with you through Zoom here. But if you back up and you take these total economic losses apart, you can find a small fraction of them, under about 50 billion of the events were insurable around the world, and that has risen to only about 1.2 or sorry, around 700 billion. But if you add back in the uninsured events, these increasing climate events really have a big impact that we need to pay attention to. Pardon me, late in the day. In addition to how much things have cost, I thought you might appreciate seeing a graph of where these events have happened. You can see the blue hydrologic events, mostly flood. A lot of them happened in South America, many of them across Asia, a smattering in Europe, and a dabbling of them in the United States. But then if you look at the meteorologic events, these are tornadoes in the US. There's quite a number of them in the United States, could burst in Europe, but these have really quadrupled. And so if you look at the latest decade, I'll just blink back and forth. That's the 80s. Here's the latest decade. You can see there were a lot of flood-related events in Asia, and down in South Africa, the flooding events happen on the Pacific shores and then the southern portion of South Africa. And what the Actuaries Climate Index do is to try and take apart where these things have happened, how much they've cost, and explain some of what's going on. So how did actuaries get involved? I thought you might like to understand a bit of what an actuary does. I have been an actuary for 40 going on 50 years. The work I do is similar to accountants, financial analysts, and these days, data scientists. The activity sectors that an actuary works in are insurance of all kinds. Personally, I'm a property and casualty actuary. That means I work on cars and trucks, houses and big buildings, but there are also life insurance actuaries, pension actuaries, Social Security actuaries, and reinsurance actuaries deal with all those sectors. What we focus on is quantifying uncertainty, measuring risk, and putting a price on it. One way I like to sum it up is, rather than going to a dictionary, here's my definition. We are the engineers of insurance who price risk. I like the term engineers because I grew up and still live in Michigan where cars are engineered. So think of all the parts that make a car go. The prices we put on risk as actuaries are what make insurance go. So when actuaries got involved in climate, seeing those big losses happen, I was privileged to be part of a team that came together from 4 North American organizations. The triangular diamond organization in the middle is the American Academy of Actuaries. They're an umbrella organization that brings together the CAS actuaries, the casualty actuaries there on the left, with the actuaries in the middle. The Society of Actuaries would do life insurance in the middle. The United States is kind of unique in the world that we divide general insurance between property, casualty, and life. The Canadian actuaries are more like the actuary work you see around the world. They deal with any kind of insurance, be it property and casualty or life. But we hired climatologists from Canada, as it happens, Solterra Solutions, and they gave us some climate guidance that we put together this way. We set these goals. We wanted to measure things related to climate across the decades in a way that educates the insurance industry and the general public on the impact of climate, that's easy to understand and not simplistic, and promote our profession. Of course, any profession would want to do that. Well, we came up with something very unique. You've seen a hint of it already in that we talk about the extreme events, the very big catastrophes. And so we turned to an important organization in the US, the Environmental Protection Agency, and saw that they were putting together a variety of climate change indicators, three kinds of them. Greenhouse gases that we peeked at a little bit when we looked at the almost million-year history. They got into climate, well, the carbon dioxide and nitrous oxide and methane and other things. They also measured weather and climate and oceans. Well, we took a look at that and says which of the things they measure are most pertinent to the big catastrophes I told you about. The CO2 measures are too indirectly tied to risk. So we started looking at things that are more direct, which are high and low temperatures, heavy rainfall, drought, long periods of dry things, or wind. And then we look at sea level. So we took those half dozen measures and we looked at the extremes, which are the frequency of severity, when severe things happen, which are rare. And we actually, if you remember your statistics, we took a look at the normal distribution and peeled off the high standard deviations, 3, 4, 5, and 6 standard deviations. And these are the child distributions, that little purple curve you see on the right. And the extreme temperatures we got measures of from the National Oceanic Atmospheric Administration, gave us very hot or very cold measures. They also gave us very wet, heavy rainfall or very dry, many days of without rain, and then extreme wind. Scientists told us wind power cubed was correlated to damage to buildings. So we followed their formula and just believed it without questioning it. And then the rising seas we got from sea level. So here are the 6 indices that we came up with. The warm temperatures and cool temperatures are the top 2. The heavy rainfall or lack thereof are the pair in the middle. And then extreme wind and sea level, powerful things, be it the powers of wind that damage buildings or waters that damage. We put those 6 things together and we came up with the Actuaries Climate Index, which you saw early on. Let me take it apart for you. Those 2 globes I showed explicitly because we divided the history in half. You can see color of the graph shows in red we have extreme hot or warming and blue cold. And we divided the years in half, and you can see we had about an equal number of hot and cold days in what we call the baseline reference period. I've already hinted at that, the first 30 years, and then we looked at how much warming has happened since relative to the swings in extremes. The extremes have tipped almost totally toward hot days. You can see there have been a handful of times when there have been cold years in the last 30, measured by the Actuaries Climate Index of Extremes. But one thing we did was we took rolling 5-year average to make some sense of the noise that the seasons, the variation of the seasons, show in this graph. And again, here are the 6 measures we chose. The warm temperatures are hot degrees measured in Fahrenheit mostly, and of course the cold days, the 10% of cold days and the 10% of high days are in degrees Fahrenheit. We could easily add that together, but then we put rainfall, which is measured in inches, together with the percent of dry days in a month. And if you're following this, we had to combine some apples and oranges, to use the old metaphor. We combine measures in degrees with rainfall and percent of days, and then we threw wind power in there and sea level measured in millimeters. And what we had to do was, guided by the climatologists, there's a list of those things. We did something called standard anomalies. We compared the changes through time to the standard deviation in those base years. And I'm not going to get very deep into the science. That's just what we did. We're actually debating some other ways. We got some insights lately from the Canadians, which I can tell you more about if you like. But that's how we combine things. Here are the 6 measures and how they come together as a simple average. T90, the wiggly red line, is the top 10% of hot days. T10, the cold days that goes downward, we actually subtract if you look close. And the precipitation is the green wiggly line. The darker brown line is consecutive dry days. And then wind power is the light tan line. And then the light blue line, sea level. We simply average those standard anomalies together to get the Actuaries Climate Index. And this is what it looks like for the US and Canada combined. We were taking a big look at the entire US and Canada, which you can see how we've colored the different states in the US and the different provinces in Canada into groups we called ACI regions. There are a dozen regions, which we'll tell more about as we go through here. 6 of them below the 48th parallel that for the most part divides US and Canada. And there are 6 US regions, a 7th in Canada, and there are 5 Canadian regions that when we take a look at these half a dozen things, we can look back and just take a look at the warming years at the end of the base years. 1990, the ACI was about 0.2, and it has recently risen to 1.2. And if we take it apart with the different component index, this cascade graph, sometimes called a waterfall graph, shows the big components of change. Sea level rise is the biggest driver through the 30 years. The next biggest is rainfall with 0.28, and temperature, if you put hot and cold together, is a little bit more potent than rainfall, but it depends on where you're looking. The southern part of the US, you're going to see more warming than you see up north where I live in Michigan. There, the cold will make a difference. And there actually is some drying going on. Consecutive dry days and wind power are actually holding down the Actuaries Climate Index a bit. And that's some analysis we can do. But when I've talked about this in different places, I heard some senators and so speak in Virginia, where I spoke probably more than anywhere else. I've traveled all around the US. Senator John Kerry was part of, as Secretary of State, John Kerry quoted him saying, "Climate change is a threat multiplier that makes worse the problems that already exist." A simpler way of saying that is the big problems that we know about are getting bigger. And the Actuaries Climate Risk Index tells how much bigger these things are happening. And so here's the challenge I've given to the actuaries I work with: come up with reliable, credible actuarial extreme risk measures. Here's a quick slide summarizing where the Actuaries Climate Index is taking root, if you will, or traveling around the globe. I've had the privilege of working with an actuary. His name is Ray Muselin in Australia. He's energized a team of Australian actuaries that have cloned the Actuaries Climate Index for North America, simplified it a little bit, and you see it gives a very similar shape and is working nicely for Australia. I've recently, as I've already told you, spoken to the Caribbean Actuarial Association. They've actually hired the same climatologists that the team of Climate Index working group I've been a part of has done to build out the Actuaries Climate Index. I've traveled to Indonesia to talk to them about the Actuaries Climate Index. The fact that we can Zoom means I can talk to you folks in Guyana and wherever else you are. That has also enabled me to talk to actuaries in Singapore that bring together actuaries in China and India and Southeast Asia. So they are talking about it. Friends of mine have talked to actuaries in Israel, and I have seen European actuaries actually take, and they have a almost instant working index based on some data put together by Europeans. ERA5 is the shorthand name for it. So that's what else is happening. I've given you a high level look at the Actuaries Climate Index, and I want to just give you another quick look and let some other pictures give you an appreciation for how the Actuaries Climate Index came together. I'm right in the middle of building Actuaries Climate Index version 2.0. And we're doing three things with data. We're looking for better input, different input, and better output that will give us some analytics possibilities. I'll give you a quick look at those, how that data will be improved. And then I'll wrap up my look today with an example of how we can quantify historical climate trends with the ACI. So here's some pictures. One problem we had with the Actuaries Climate Index was very coarse data. This is just the southeast side of the US. You can see there are just a handful of points. If you look at Florida, where I lived, we mapped it at one point. I lived in Florida, and it's kind of annoying as having been a Floridian for 5 years to say, we missed. We had 6 points in our data that should have hit Florida. Only 3 did. Well, it turns out in the states above Florida, Georgia, Alabama, but more importantly, up along the Atlantic coast, Virginia, South Carolina and North Carolina, a higher percentage of the points hit, but you can see 3 more points missed. So our solution was to use a finer 1 degree by 1 degree. This is only 2.5 degrees, a very coarse grid. What's that improvement look like? Here's the 1 degree grid and how it covers North America. You can see the improvement going from a 2.5 degree latitude, longitude grid to a 1 degree grid. We'll get a whole lot better coverage. We're actually diving deep already into ERA 5. They're going to do a 1/4 degree by a 1/4 degree grid. You can see that do real nice coverage, but you can see we're getting finer coverage. Another thing we're doing is trying to get more complete coverage data through time. This is the sea level history that we've got by month. The blue wiggly line here shows for the Central East Atlantic region of the US. That's Virginia, North Carolina, South Carolina, and thereabouts. You can see how the sea level rise by month wiggles up and down as the moon circles the globe. You have the obvious swings of the high tides and low tides, but the ACI only looks at that 5-year average in the middle. So we're hoping to find ways to take that monthly signal and take better advantage of that kind of thing, a finer slice through time. So that's another look we're trying to do. And then we're also looking at different data back to these possibilities from the EPA. The EPA turned to the National Oceanic Atmospheric Administration, which you might like to know is headquartered in North Carolina in a city called Asheville. I've made an annual trip to Asheville and gotten to know the scientists that house the data there. They literally have petabytes of data. And the Europeans who have done some satellite work are also gathering lots of data. So we're revisiting the 6 simple indices and choosing different ones. The last point I'll make here is the bottom item. We are looking to get more detailed ERA 5 data, that's land data from the Europeans, but they've also collected ocean data instead of global historical climate network data. That's what we're using now. So that's a preview of coming attractions. And then when we get those finer grid data, we will go from the 12 regions of the US to downscale the work we do from climate regions which follow the mountains somewhat. I can see the mountain ranges having lived across the US and the regional climate structures on the left. We're going to downscale from those regions to states and even finer to counties and cities. As you think about doing that, say in South America, you're going to talk about countries and cities and the like. But one thing I noticed along the way that was just a real curious thing was this snapshot. By visiting scientists in Asheville, North Carolina at the National Oceanic Atmospheric Administration, they have a national climate environmental information thing. About every 30 years, they do this snapshot look and how fast is sea level rising. And this is a snapshot look. And they've put arrows in the different coastlines where there are tide level gauges. And you can see the shorter arrows are about 3 millimeters per year. The longer, mostly yellow arrows are 3 to 6 millimeters rise a year. And then there are not too many 6 to 9, but there is like a red arrow in the middle of the Gulf that's right there in Louisiana, because as the globe spins, the Gulf of Mexico acts kind of like a baseball glove. And so it kind of catches the waters that flow in through the Caribbean into the Gulf and hammers Louisiana and the eastern part of Texas and the panhandle of Florida a whole lot. But then along the Atlantic coast here, you can see they've got pretty much a 3 to 6 level, 3 to 6 millimeter a year rise in sea level, but only a 0 to 3 millimeter rise on the Pacific coast. But then something really weird is going on in Alaska. The sea level appears to be decreasing, and decreasing not at a short or a slow race, but decreasing at a very fast pace. And then something like that is happening in the Hudson Bay and up here in the northern eastern side of Canada. So that got me thinking, well, what's really going on? Can we do something with the data from the Actuaries Climate Index? Well, we have 12 regions. So I looked at them and said, 4 of them are on the Pacific side and 4 of them are on the Atlantic side. So let's ignore the ones that are in the central part of Canada here. CIR, the Central Arctic, NPL, the Northern Plains, the Southern Plains, which is in the center part of the US, and where I live, the Midwest, we kind of ignored that. But then I focused on what's happening in the Pacific and what's happening in the Atlantic with sea level rise. Starting on the Pacific side, because Alaska is there, here is the sea level rise data, which you can see from Alaska really stands out, decreasing at over 6 millimeters a year, whereas most of the Pacific is rising at 1 millimeter or 2 a year, maybe faster nowadays. But now let's turn to the Atlantic. In the Atlantic, here we've got the Southeast Atlantic and the Central East Atlantic, and even the Northern Atlantic part of Canada rising at solidly more than 3 millimeters a year. But the very northernmost part of Canada is also dropping. A lot of noise in the data, but it's clearly dropping. So then I said, can I extend this worldwide? Well, it turns out the Actuaries Climate Index is using tide gauge data that covers the entire globe. I don't show this on the little graph here, the green graph with blue dots, but there are 76 guide stations in the US. You can see the tide gauge stations that I was able to go and grab elsewhere in the US, a lot of them on the Pacific side of South Africa, or South America, sorry. Many of them in Europe, a lot on the eastern side of Asia. But then I added some new information, ice melt. There are funny named organizations that I can't recall the name of. You can see the acronyms there. But putting these two sources together, I look back at the global history of tide gauge data and looked at and fit a trend line to the global information. And you saw in the base years, it's got a pretty steady trend that projects out into the last 30 years, but something's happening in the more recent 30 years. And what's happening is ice is melting both in the Antarctica and in Greenland. And that is what was tracked by the Europeans and the ESA, and comes together with the IMB organization and NASA in the US, from whom I got actual ice melt data. And there are 4 trillions of tons of ice being melted. Well, when I fit that data, you can see that data actually explained the increase globally. And then I started to ask that question, what's happening in Alaska and the northeast part of Canada? And first look is in the Atlantic Ocean, where Greenland is melting, and Greenland is melting faster than Antarctica. So lo and behold, the permanent mean sea level rise data actually is predicted to have a higher pace of sea level rise in the Atlantic than the Pacific Ocean, because the Antarctic is melting slower and mostly going into the Pacific, which is much bigger than the Atlantic. So then, having looked at those 2 biggest oceans, I started asking east and west coast of the Atlantic. And essentially I found either side of the Atlantic, the increase in sea level rise is happening at the same pace. Not a lot of difference, a slight difference in the Americas, where I live and where you folks in Guyana live. The Europeans are seeing a slightly faster pace. And then if you look at the South Pacific and the North Pacific, there again, that ocean is so big, the pace of sea level rise is about the same. But now if I put everything together and look at the sea level rise variation by latitude, here in the Arctic, there's a slight increase, not a lot. But then if you put Alaska in, that's where this sea level appears to decrease. That's Alaska and a few stations in Russia and so on. But now if you look at America and southern Canada and Europe, you can see the increase is at that pace. Now along the equator, or the northern part of the equator, that's the pace. Right at the equatorial pace, lo and behold, at the latitudes of the equator, we have probably the highest pace of sea level rise. And at the southern part of South America and the southern tip of Africa and Australia, it's a little slower and slower again. But the experiment I did found the hypothesis that the NOAA map suggested showed me sea level rise is happening fastest near the equator. And why? I think what's going on is because more equatorial water is squeezing the globe. There's just so much, trillions of gigatons of water have melted, that when the globe is squeezed, there's more place for water to fill up around the equator, but land is actually rebounding in the levels of Alaska and Russia. Alaska is where it's most noticeable because there are more stations there, and that's why it seems the sea level is actually retreating there, because there's a land rebound. But point being, I could not share this with Thomas when he reached out to me because of the volcano you had explode. Not too long ago, this came to mind, and so that's why I shared it. And there's my look-see at the Actuaries Climate Index and some things it can do, things it might do. And with that, I'll take some questions.